All right, welcome back to ysics 3030, and today we are going to continue our technical discussions to the lecture 2. And if you have any questions during the lecture, please unmute yourself, or you can type in your question through the chat box. All right, so the lecture 2 is about the resistor metals and interconnects. So we are going to briefly discuss the physics of those components on the integrated circuit. And the reference for the lecture is this reading material, Modern Semiconductor Devices for Integrated Circuits. And as we announced earlier, so this book is freely downloadable from Professor Hu's webpage. And also for your convenience, I uploaded the PDF chapters to the Canvas. And for this lecture, the reference chapter is section 2.21. And also the recorded lecture from the last spring semester available here, and also the pre-recorded lecture by Professor Asif Khan available in this YouTube link. All right, so let's talk about the resistor on the integrated circuit chips. So as we discussed in the introduction, the device components, like the transistors, are built on the substrate of the silicon. And then we need to collect different devices through those wires. And those wires are made of the metal. And we call the connections as interconnects. And those metals will be collecting different devices through this kind of routing network. So actually there are many layers of those interconnects on the chip. So here we see this kind of cross-sectional view of the chip stack, where you have the transistors on the silicon substrate, and then on the top we will have those wiring. Of course, here if you cut a slice of the chip, you will see this kind of cross-sectional view. So here this kind of brown color represents the wiring, which is the metal. And typically there are more than 10 layers of the interconnect layers. And the bottom 1, 2, 4 is called the local interconnect, because you only talk to the neighboring devices. And then if you want to travel further to other part of the chip, then you have to utilize this global interconnect, which is typically above layer 8. And as you can see here, those wiring will have different dimensions. Typically, as you go up, the wire pitch will be larger because you have to travel longer distance. So you have to make the wire, let's say, a little bit wider in the dimension, so you can reduce the resistance. So you can reduce the RC delay when you transmit the signals for further distance. And here on the bottom right figure, we show an image from one IBM chips. So here you see that actually there are many interconnects, and it's very complicated in a very, let's say, advanced technology node. Then you have many of those wires, and you can think those are like an overpass of the highway. Then the signals will travel from one location to another location through those wires. So any questions here on this slide? So if you have questions, please type in here in the chat. We can continue. So here we want to show one example of a real chip design. And here you see this layout of the block tree for this chip. So this chip is a chip for the AES encryption. So this is a standard way to encrypt the data these days. So this is the way you encrypt your password or encrypt your Wi-Fi communication. So this is the standard way to encrypt the data, and actually this can be implemented in the digital circuits with like 120,000 digital gates, or we call it cells. So one cell can be, let's say, a NAND gate, NOR gate, or this inverter, NOT gate, or two inverters will be a buffer. So you can implement this kind of AES algorithm into the silicon chips with those gates, and in total, we may have like 700,000 transistors for this encryption engine. So here this figure shows the clock tree. So you need to deliver the clock signal to those 120,000 cells across the chip, because each gate will be controlled by the clock signal, and you need to deliver the clock signal across the whole chip. So you need wiring to collect different parts of the chip together through this clock tree. And here you see this is a very complicated routing. And then you see those cross points. Actually, that means you cannot finish this kind of routing at the same layer of the interconnect. You have to build an overpass. So you have to utilize different layers to finish the routing. So this is just one example to show the complexity of the interconnect. Okay, let's look at this microscopic image again. You have seen this in the last lecture. So this is the cross-sectional view of Intel's Broadway CPU at 14 nanometer node. And again, the bottom substrate is a silicon, and silicon is a semiconductor material. And here then we know this is the MOSFET. We're going to discuss this in more details in the later lectures. But today we're going to focus on the wires here, those interconnect wires. And between two layers, we will build this contact via. This is called a VIA, via. So this is the connection between two layers. And here we have more than like 10 layers in this design. Because the signal routing is so complicated, then you have to utilize multiple layers to finish the routing. Okay, so if you think about the total length of the wiring, the wiring of this CPU, if you unroll, let's say, all the wires into a single line, and then if you measure the distance of this single line, it can be more than 10 miles. So this is hard to imagine for microprocessor, which is like only a few millimeter square. And then, but if you unroll all the wires into a single line, it can be very long. So here we have some data for different technology node. Here, like in 2001, the technology node at that time is 130 nanometer. And then as we scale down the technology to 65 nanometer, this was introduced in 2007. So the transistor count per chip increases. So here is in the unit of million. And then the transistor density also increases. So that is the transistor count divided by the chip area in the centimeter square. And but the chip size is kept the same. So this is the Moore's law. Even with the same chip size, we are going to pack more number of transistors on the chip, because the transistor dimension will get reduced to 0.7x per generation. And here's another number is this, let's say, the number of metal layers. As we scale the technology node, then the design may become more complicated, so we need more layers to finish the routing. And if you unroll the wires, here the total interconnect length, you can see here the unit is mile. You can reach like 20 miles in this 65 nanometer processor. So this is pretty long. And then what we care about is the RC delay across, let's say, 1 millimeter line. And here, for example, in the 65 nanometer design, if you measure the RC delay, that means if you transmit a signal, let's say a rectangle pulse from the starting point to the ending point, let's say with 1 millimeter distance, you need to spend like 300 picoseconds to do that. So this will eventually limit your clock frequency if you do nothing between those starting points and ending points. Then you need to use 300 picoseconds to transmit the signal. And 300 picoseconds, if you convert that to clock frequency, is about 3 gigahertz. All right, any questions here? Let me check the chat because I cannot view the chat during the full screen session, so I have to exit the full screen and then occasionally check this. If you have any questions, feel free to ask. All right, let's go back. So here, this slide shows the typical circuit elements we used for the integrated circuit. And we can have two kinds of elements. The first one is the linear circuit elements, like the resistor, capacitor, inductor. And I believe that you have learned those circuit elements in your 2020, not 2020, maybe 2040. So the RC, for example, RC circuits. And in this course, we are going to learn more nonlinear circuit elements. For example, here we have this p-n junction-based diode. So basically, the current will be unidirectional. So you can only flow the current from the left to the right in this device. So we will discuss how this device works in more details, maybe in the lecture 7. And then, of course, this is the transistor, the building block for the integrated circuits today, which is called the MOSFET, metal oxide semiconductor field effect transistor. And this is a circuit symbol of this MOSFET. So this is a typical transistor we use today for the digital circuit, and we will learn great details in this course. We will spend quite a few lectures on this topic, so we will discuss that later. And if you look at the materials we used to build those circuit elements, for the resistor, we just need the metal. So the metal will have finite resistivity, and if we define the geometry of the metal, like the length or the width or the height, then we can define a piece of resistor. And for the inductor, we typically don't use that for the digital circuit. Inductor may be used for the analog circuit. If you want to build, for example, resonator, you may want to use inductor. But in this course, we're not going to deal with inductor. If you want to build inductor on the silicon, actually, you just need metal wires. So the way you build the inductor is typically you can have, let's say, some wires in this kind of spiral shape. If you define the wires like this way, and you know if the current flow, if you have AC current flowing along this wire, you know the AC current will generate the EM signals. You can use, for example, right hand rule to do this kind of EM signal generation, right? So if you have, let's say, on your right hand, and then you have currents flow in, then you will generate the magnetic field. So this is a way to build the inductor, but we will not discuss that in this course. And then for the capacitor, you may need the dielectric or the oxide material because you need to build the structure, typically like a metal oxide metal. If you have, let's say, a sandwich structure, you can have metal, and the oxide in between. So the oxide nominally is insulating, so you can build a capacitor across that. This is like your plate capacitor. And you can build that on the silicon as well. And then for the MOSFET, we need to use a semiconductor. So that is why we have MOS, metal oxide semiconductor transistor. So in that case, we need the silicon substrate, and then we need the, let's say, the metal and oxide. So this will become a MOS structure. We'll discuss that more in great details in the lecture 8. So today, we are going to focus only on this one, the resistor, because that is the basis for the interconnect. Alright, so let's look at the resistor. So maybe from your high school physics, you know that this is the symbol for the resistor. And I assume everybody knows this equation. So what is that? This is called what? Well, this is called Ohm's law, right? So this is your Ohm's law. Voltage equals to current multiplied by the resistance. And we are going to derive some equations in this following slides. And here what we want to do is to correlate the physical picture from the macroscopic view to the microscopic view. So what is macro? So here, if you look at the piece of resistor, you can see it. So it's macro. And then later, if we consider the electrons, which you cannot see it from your eye, from your bare eye, so we call it micro. So we want to link the physical picture from the macro point of view to the micro point of view. So let's do that. So here the Ohm's law, we can derive a few equations based on the Ohm's law. First, the electrical field, by definition, is the voltage divided by the length of the resistor. If you think about the length of the resistor is L, and the voltage across that is V, then the electric field across this resistor, by definition, is the voltage divided by the distance L. And then the current density is defined as the current divided by the cross-sectional area. So for example, you look at here, we have a piece of resistor, and we have this length L, and also we have a cross-sectional area A. Of course, A equals to the two sides, the product of A and B. So the current density is how much current you flow through this cross-section divided by the cross-sectional area. So the current divided by the A is the current density J. Okay, so then we can link those two equations back to the Ohm's law. What you can have here is, for example, V will be L times E. So then you can get back to here, the Ohm's law is L times E equals to I times R, and I here is A times J. So then you can substitute this I with A times J, and then divide by A. Sorry, it's A times J, and then you have the resistance R. So eventually you can get J equals to, if you move the terms around, if you move the A and R to the other side, you will get this equation. So here we can define this J to be equals to sigma times E. So here sigma is this L divided by AR. So what is sigma here? Sigma is actually conductivity. And you know conductivity is 1 over resistivity. So sigma is 1 over rho, if the rho is the resistivity. So you can get 1 over rho equals to L divided by A times R. Or in other words, you can derive R equals to the rho times L divided by A. And I assume that you may be familiar with this equation. So this is just the equation to calculate the resistance for this piece of resistor, where you have the cross-sectional area A, this and the length L, and then rho is the resistivity of this metal. So far this derivation is still based on the macroscopic view. Any questions so far? Let me see. Right, so far so good. So here let's move to the second slide. So basically I have the summary of the derivation here. This is what we just derived. And now let's look at the microscopic view. So what is the microscopic view here? So in this piece of metal, what is really carrying the current is the electron. For example, if you apply voltage V across this metal, then electrons, you know, will flow to from the right to the left, because electrons, you know, is negatively charged. So it will go to the positive bias, which is the left side. So there are many electrons moving in this piece of metal. And if we consider a time, let's say dt or delta t, a short period of time. So the distance for the electrons to travel is the velocity of the electron multiplied by the time. So V times this dt is the distance for the electrons to travel in this period of time. Then here we can consider, here we have a volume here. So there are many electrons in this volume. So the total charge Q in this cube will be the density of the electron. So N we can call it electron density. So that is the number of electrons in the unit volume. So this is number of electrons in this volume. This is density. But if we want to get the total number of charge, then we need to multiply the total volume of this cube. So the volume, you know, is the product of the three sides, and then the cross-sectional area is A, and then the other side is the V times dt. So this is the volume, of this cube multiplied by the n. So then this will be total number of the electrons in this cube, and then multiplied by q, because each electron will carry the charge q. Q is a physical constant, that is the charge quantity each electron carry. If I recall correctly, it is 1.6 10 to the minus 19 coulomb. So this is the charge, basic charge quantity. Okay, so this is total charge in this cube, and by definition, current is dq over dt. Why is that? Because current is the number of charge flow in a certain period of time. So this is by definition. And then this actually is a dq because it's dt in the short period of time. So this is the charge in that short period of time. Okay, so then you will get the qNAV dt divided by dt. So this dt will cancel each other. So you will get qNAV. And then the current density is I divided by A, as we see here. So then if you move that A to the other side, so what is left is only qNV. So basically here, this is a microscopic view of the current density. So basically current density is determined by how many electrons in this volume. So that is the density n times how fast electron move. That is the velocity of the electron v. Of course, you need to multiply by the q, which is the charge quantity. So this is the current density, and then you see here we have the current density derived before from the macro point of view, and here is micro. But essentially they are the same. So you can make those two equations together if you think the link is the J. So sigma E will be QNV. And then we can move this around. So then it will be, you move the Qn to the other side. So it will be Qn sigma E. So here we will define this sigma over Qn as a new variable. We call it mu. Mu equals to sigma over Qn. So then V equals to mu E. So what is this mu? Mu is called mobility. Also here I need to make a correction here, because current flow in the opposite direction of the electron by definition. So you need to carry a negative sign here. So here you have a negative sign. So this negative sign is for electron flow and current flow. By definition, they are opposites. Okay, so this is the final conclusion we want to draw. The velocity of the electron in the metal is proportional to the electric field in this metal. And this coefficient is called the mobility. So this is what we want to derive here. I know it's a little bit tedious, but hopefully you can go through this one more time after class. And let's have a summary in this slide. So this is what I derived in the previous slide, but it's clearer, more clear than my hand calculation. So here you have the summary. Velocity of the electron equals to the mobility mu times the electric field E. And in other words, here this mu is sigma over nq. This is by the derivation. Or in other words, sigma is nq mu. Sigma is this conductivity here, and n is the electron density, and mu is this mobility. So here this negative sign, as we just said, is due to the opposite flow of the electron and currents by definition. All right, I want to stop here and ask if there's any questions during this derivation. Okay, so yeah, so the dq, yeah, we consider the short period of time, so the charge to be dq. Oh, one more. What is the negative sign for? Okay, so the negative sign is for the current flow is in opposite to the electron flow, so the velocity will carry a negative sign, because by definition the current, let's say here you see that this, if you have positive voltage on the left side, negative voltage on the right side, the current by definition is from the left to the right, but the electron is moving from the right to the left, so you have a negative sign. Any more questions? Okay, so let me try to stop recording for this part 1. I want to break up the sessions into multiple.